Hello everyone. Welcome to the virtual LISA21 conference. My name is Devon Bautista, and I am a postmaster's researcher at Los Alamos National Laboratory, fresh out of grad school, and I have been researching the management and provisioning of HPC clusters at a systems level. I am coming at HPC from an operating systems perspective, and today I will be speaking on behalf of myself and my co-author, Lowell Wofford, on more performant cluster state management using open source firmware and a Kraken. Before we begin, I'd like to go over a little background on firmware and how we got to where we are today. Firmware has a long and progressive history, similar to that of operating systems. In the old days of booting 20 plus years ago, firmware was comparatively dumb at booting operating systems. MBR booting would typically give control to the first bootloaders able to read without error. There is typically no verification of the bootloader except for example, its signature in the last 2 bytes of the boot sector, as in the IBM PC-compatible BIOSes. The firmware images were typically proprietary to the board, of course, obviously, and open source alternatives, however, appeared later, namely coreboot and libreboot. There were several limitations of the BIOS MBR method of booting, including the operation in 16-bit real mode with no memory protections and no virtual memory. They had to operate within a 1 megabyte of addressable space, and the images were typically programmed in assembly language without the benefits of using a high-level language. They could only address hard drives or any storage media up to 2.2 terabytes in capacity, whereas today's firmware supports on the order of zettabytes of data. Intel created the Extensible Firmware Interface specification in 1998 to eliminate these limitations as a goal. EFI passed on to the Unified EFI Forum in 2005, and the UEFI Forum continues this specification today as the Unified Extensible Firmware Interface. Notice that UEFI is a firmware interface, a specification rather than an implementation. There are several implementations of the UEFI specification. But as a result of the second system effect, UEFI is pretty complicated. You've probably seen this diagram before if you've been to a firmware or security conference in the past decade or so. These are the boot phases of a UEFI-compliant firmware image. First, we have the security phase, which cryptographically sets up the pre-FI initialization phase and verifies it, and then hands over control to it if it's verified. The PEI then sets up critical low-level things, like the memory controller and CPU interconnects. This stage is very limited up until then, and there is no DRAM or caching. On x86 systems, each core comes up thinking it's in 16-bit real mode, and so this phase sets up memory paging as well as virtual memory. Next, the DIXI phase, or driver execution environment, enumerates buses and initializes other devices that are connected to the system. This is where UEFI option ROMs are executed, and it's worth noting that most UEFI firmware image code lies here, and I'll discuss a little bit more on that later. Next, the BDS determines which disk, device, or network to load the OS bootloader from. The OS bootloader lies in TSL and is actually not part of UEFI, but this is something like, for example, the Grand Unified Bootloader or GRUB on a typical consumer Linux system. Then the final bootloader calls the runtime, which is where the OS, final OS, is located. Since UEFI firmware is pretty ubiquitous both in the consumer world and server world, it is the type of firmware that I will be discussing in this talk. So, I will now discuss the trend towards moving towards open source firmware. So as I said before, the DIXI drivers tend to take up the most substantial portion of the typical UEFI firmware images. Here is a list of DIXIs from the Intel S26000 from 2017 that was discontinued in 2019. This slide was taken from Trammell Hudson's 34C3 talk on Linux boot, which is a talk that I have referenced a lot of the security material from, and it is one that I highly recommend watching and reading in order to learn more about firmware research and security. Do see the endnote number 1 in these slides for more information on that. Note that there are over 400 of these modules, which is a substantial amount of code. A lot of these are even polling I/O driven, slow, and primitive, and that is one reason why UEFI tends to boot more slowly. Now, I don't bring up the size to complain about how much space it takes on the chip, but rather to bring attention to the greater attack surface. Note that there is a full network stack present, in this case likely for Intel's management engine. Now, as an aside, there are plenty of known vulnerabilities in the management engine, and if you want to learn more about those, see the master's thesis of Vasilios Ververis, who does a very good security analysis of the ME. I have referenced that as endnote 2 on these slides. But this network stack contains both IPv4 and v6 drivers, and as we've seen in the past, network stacks tend to contain unknown 0 days. There's also legacy device drivers, floppy disk drivers, ISA bus compatibility drivers, etc. And it's these dusty corners that raise the potential for vulnerability exploitation. For example, those that were discovered in the Xen hypervisor that allowed breaking out of its sandbox. There is also option ROM setup, and option ROMs can actually be quite dangerous. For example, the Thunderstrike bootkits that allowed the Thunderbolt option ROM to flash untrusted code onto boot flash and even propagate to other devices. There is also vendor boot logo loading, which in the past buffer overflow vulnerabilities have been found, and as well as the ambiguous things like Microsoft OEM activation or Y2K rollover, which, going off of the name, has that driver been updated in the past 2 decades? So here is a diagram of the more realistic privilege rings on a typical x86 system. You've probably heard of the more conventional privilege rings, but this diagram was taken from Ron Minnick's 2017 talk from the Linux Foundation's Embedded Conference in Europe, which is another talk I highly recommend watching. Ron is a software engineer at Google who gave this presentation advocating open source firmware, and he exposes some of the horrors of the x86 platform. So in Linux's early days in the 90s, when the i586 was popular in the days of BIOS and BR booting, Linux controlled most everything about the x86 architecture. But in the age of UEFI, this is no longer the case. There are now 2.5, what are essentially kernels, between Linux and the hardware. Ring 0 houses the Linux kernel, or supervisor, which is what most everyone is familiar with. It historically has the highest privilege ring, hence 0, but as technology has advanced, we've run out of ring numbers, and so we've gone negative. And so in ring -1, we have the hypervisor, or supervisor of supervisors. This traditionally is what is supposed to have the greatest privilege over the hardware itself. But we also have now ring -2, which has UEFI and SMM. System Management Mode, or SMM, is a privileged x86 operating mode created by Intel to perform system-wide functions such as hardware control or running proprietary OEM-designed code. It is entered through what are called system management interrupts, and it essentially takes over the machine to provide power management functions such as suspend when an operating system, such as DOS, didn't support it. However, other interrupts can be handled here as well, such as USB. So if you've ever have plugged in a mouse into a machine where the OS didn't support that particular mouse but somehow it worked, that was probably because of a USB stack in SMM that didn't support that mouse, independent of all the other privilege rings. SMM isn't really a full kernel, a half kernel, rather, since it technically traps into 16-bit real mode with no memory protection, multitasking, or privilege levels. But it can completely suspend the operating system, without its knowing, and exit into UEFI. UEFI boots the operating system, but it has these applications that run alongside it, and the operating system will trap into it when certain hardware events or interrupts occur. And then we have ring -3, and this houses the out-of-band management like the Intel management engine. This can actually reflash your node if connected to the network, even if the machine is powered off in some cases. It contains a full network stack just like UEFI, and is independent of all of the other privilege rings. So, for something whose job it is to boot an operating system, it seems to act more like an operating system, and not just one, which seems like a good way to maintain vendor control over you and your systems. Now, I pick on x86 because that is what most consumers and commercial users are using, and have been for decades. But also because Intel was the creator of what has become UEFI, and the x86 platform, which Intel created, typically tends to be more locked down in regards to firmware versus other platforms like the ARM architecture, which tends to be more open in regard to firmware. However, getting away from this is no longer as simple as, quote, switching to AMD, who, by the way, has had its ME equivalent called the Platform Security Processor, or PSP, since 2013. So here are just a few examples of redundant drivers that get loaded on a typical Linux system that I've been talking about. And these are just the open source variants. So we can see that we have fat file system drivers in firmware, the bootloader, and of course, Linux. Now imagine if there were a compromise in either the firmware or bootloader. One could potentially gain persistence before Linux even boots, and persistence in firmware means persistence on the flash chip on the motherboard, which is extremely difficult to remove besides just getting a new board. This is unlike the OS, where one only need to reformat the disk, and all is well. All three of these also have USB stacks, and different implementations of USB stacks means different support during each boot phase. And unfortunately, USB stacks tend to be both common and complex. A buffer overflow in a USB descriptor handler, for example, could cause a rogue device to be plugged in and take over the boot process. Finally, all three of these also have network drivers, which allows the possibility of remote exploitation at 3 different points in the boot chain. Note that a full compromise is possible only with the weakest link in the boot chain, and successful exploitation at this link leads to control of all of the subsequent phases in the boot chain. Now there are obvious problems with this, and these include that the same hardware is operated on by differing drivers, most of which are closed and proprietary. This means that they don't get the same scrutiny and independent attribution that a widely used open source project would get, such as Linux. All of this extra code, as I discussed earlier, tends to increase the attack surface of the board's firmware. And yes, UEFI vulnerabilities have already been found which can be persistent, since it runs at a higher privilege ring than the operating system. And this is actually one reason why an attacker would want to attack the firmware in the first place. And if you can control the firmware, unfortunately no OS patch is going to save you. Loading the system, or the same drivers, is also slow. Vendors will tend to try and support a multitude of hardware by including many drivers for heterogeneous devices, and understandably so. And this is fine if time isn't an issue, such as when you're booting less frequently, like on consumer systems. But when you're booting finely tuned hardware that is benchmarked and high performant, and these nodes reboot quite frequently, this may be a problem. The code that initializes the hardware and boots the operating system, or even runs alongside it as an UEFI, tends to be audited and scrutinized the least, being just internal to a company typically versus open source, and it is often updated most infrequently. The comparative difficulty and rise in effort of updating firmware on systems compared to the operating system software updates makes it more likely for a lot of the same systems to have out-of-date firmware. So in essence, the code that can fully control the hardware in OS is looked at by the fewest people and is updated the least frequently compared to software and operating system. Finally, the reliance on the vendor for updates is often very slow and tedious, and it often misaligns with production timelines and tends to bottleneck the workflow. Board manufacturers also frequently outsource firmware development outside of the company, offering yet a middleman to jump through when you're dealing with firmware bugs or problems, or even just updating your firmware. So, all of this can seem very scary. So, what is being done about it? What have companies done about it? Well, a solution that companies such as Facebook and Google have adopted is a project called Linux Boot, which replaces most of the UEFI Dixie drivers with a Linux kernel in order to use production-ready open-source Linux drivers in firmware rather than the proprietary vendor ones. Although one still needs the firmware blob of the board to get Linux Boot to work, the binary PEI that is very board-specific to initialize the hardware, one can essentially customize what is already a minimal OS into one that is as simple or as complex as what one would need to boot for one's boot process using a customized kernel and initial RAM disk. Now, even though Linux Boot has only relatively recently been adopted by these companies in the past decade or so, or half decade, the idea of Linux in firmware is actually not a new idea. The project itself takes its inspiration from the Linux BIOS project that was started at Los Alamos in 1999 by Ron Minnick, which was aimed at replacing proprietary BIOSes in HPC systems with a faster version that would perform just the minimum amount of tasks required to get a system running. It was used on the third fastest supercomputer in the world in 2003 according to the Top 500 list, and it became the more well-known project Core Boot in 2008. Which removed the Linux component due to decreasing sizes of flash chips at the time in favor of a more generic board initialization that was capable of booting more generic payloads. However, flash sizes have on average grown again with the growth of UEFI, and so Linux Boot returns to the original idea of Linux in firmware. With Linux in firmware as well as the operating system, we now have a single implementation of drivers. Further, the proprietary drivers that were contributed to by tens to hundreds of developers and have only been tested internally are replaced by open source drivers that have been contributed to by thousands of developers across the world and have been tested on widely heterogeneous systems for over 2 decades. Another benefit that I will expand on subsequently is the ability to tune one's bootstrapping mechanism to one's site-specific needs. Further, more people understand Linux in general than firmware. Our researchers and engineering teams are already used to working with Linux, and so bringing it into firmware reduces the need for firmware engineers. The tooling also tends to be more mature than a lot of the UEFI ones, for example, the UEFI shell. Why learn a new shell and more tooling when you can use Bash or whatever Linux shell that you're using and that you use every day? And so if Linux in firmware and more generally open firmware is not a new idea, then why am I bringing it up? Won't vendors just flat out refuse it? Well, open firmware, like open source software, has been gradually permeating the industry. Take Facebook, for example. In 2011, the Open Compute Project was announced as an open hardware initiative that shares data center designs among a consortium of companies. The Open BMC project then was created in 2014 as an open implementation of baseboard management controller firmware and it is now a Linux Foundation project. It's worth noting that under the hood it actually uses a Linux kernel, which is another example of Linux in firmware in the wild. But most notable were talks in 2018 by Facebook engineers David Hendricks and Andrea Barberio at LISA and the Open Source Firmware Conference. In these talks, they admit that booting is hard. In other words, engineers and administrators have to deal with many heterogeneous types of devices nowadays instead of one de facto standard as it may have been in the past. They acknowledge that there are a lot more demands for security these days in all types of software that really wasn't there 2 decades ago, and they apply this idea that needs to be present in firmware. For example, being able to have a cryptographically verified bootstrapping of many nodes would mean that silent corruption, or more seriously, malicious tampering of the OS image, can be avoided, or even at least just detected. Provisioning tends to be more complex nowadays, especially now that firmware is not as simple and does one thing but has become more of an operating system. Or if you're Facebook and you have many data centers worldwide, and you could be provisioning nodes that are across the internet rather than across the room. And so there's a need for something more robust. And this is especially relevant in HPC, as I'll discuss subsequently. When dealing with firmware and firmware development, one is normally accustomed to working with binary blobs, such as Intel's Firmware Support Package, or FSP, on Intel platforms. In the mid-2000s, though, Intel made the core of their firmware open source in the form of the EDK and EDK2 package. However, one still had to call into the Firmware Support Package, or FSP, which is an opaque binary blob that was and is closed source. But Intel recently announced their gradual transition of making various board components open source that were previously closed, and this includes the FSP. This is according to Michael Kubacki, who presented this at the Open Source Firmware Conference in 2019 as an Intel employee. He announced this with the rollout of the minimum platform specification, visualized in this diagram, which is an open specification that allows developers to more easily develop platform initialization for a wider variety of Intel silicon that support this spec. But this isn't a firmware engineering talk, so if you want to know more about the Min platform or Intel's open sourcing strategy, do watch Mr. Kubacki's talk, which I've included in the slides as EndNote 6. But the importance of mentioning the minimum platform specification and Intel's open sourcing strategy means that open firmware is now becoming a more commercially viable option, since this may now influence other vendors to do the same. And since ARM has been getting into the HPC scene now, I wanted to briefly bring up that ARM has also been an active contributor to the EDK2 repository. And the ARM microarchitecture tends to be more open towards open firmware than more ubiquitous platforms like the x86 platform. So, now we move on to open source firmware in HPC specifically. So there are some needs in HPC that motivate the move to open firmware, and I'll discuss those now. In any computing situation, one would typically want to boot their systems as quickly and as efficiently as possible. And no one knows this more like HPC environments, who typically need to do so the most. In order to achieve this, we need to be able to customize the system initialization. This means that from hitting the power button to starting user jobs, we would like to be able to control how that is done. The reason for this is apparent. Custom init means experimenting with different methods to obtain the most performant and robust booting method for that particular system. The HPC world does care about boot times because nodes can crash and reboot quite a bit more often due to the heterogeneous and often demanding nature of user jobs. Unlike the world of the cloud, jobs can't be migrated for maintenance or operating system upgrades due to the isolating structure of clusters. Jobs in the web world can easily be migrated between systems due to virtual machine and container technology, but physical systems still need occasional maintenance. Further, the firmware on vendor boards typically is designed to accommodate a wide variety of use cases and to support many different devices, which is why modern firmware boots typically more slowly than it has to, because it has to check and load all of these drivers. HPC nodes don't really need all of the possible supporting features that generic firmware offers, but rather only the specific drivers and features that it needs to do to get what it needs to do done and no more. The HPC nodes in theory have a simple lifecycle. They turn on, contact their parent, get provisioned, and execute jobs. And so having a firmware image that is tuned to that particular purpose and that particular use case is ideal in this situation versus a generic option. Also, the standard protocols that most firmware comes with for provisioning stateless nodes include, for example, TFTP, which was developed in the 1980s, as well as DHCP. Typically after power on, the firmware will execute DHCP to obtain its IP address, then execute TFTP to pull the OS image, which it will then execute, exiting from the firmware space and switching to software space. The problem, though, is that different implementations of TFTP and DHCP can be buggy, from both different vendor implementations and differing versions of the same implementation from a vendor. So it would be useful to control the implementation in order to run it, fix it, and improve it in our own schedule, rather than having the vendor basically dictate which version for us to use. With open firmware, one could even use a more modern protocol such as HTTPS to obtain images, offering an additional layer of security through encryption. And speaking of security and cryptography, since compute nodes typically have a simple life cycle, namely to look for their parent and be provisioned and start work, one could take advantage of open source firmware to, for example, store a TLS client certificate in each node, perhaps in the TPM if it's present, as more hardware is supporting nowadays, in order to provide a sort of access control to the parent. That is, only trusted nodes can be a part of the cluster and can be able to connect to the parent. We would also like to be able to run an extremely minimal operating system on compute nodes, since nodes typically have a narrow focus, like I discussed previously, and we would like to eliminate any potentially latent extra layers. For example, we would prefer to take advantage of containerization for jobs, but be able to do so directly on top of hardware, so that we can reap the benefits of containerization, but with the performance of working directly with hardware. Finally, we desire to run a cluster state manager as early as possible in the boot process for more granular hardware control. With open firmware, we can include our custom provisioning solution within the firmware image, so we don't have to wait for the vendor image's generic boot process to complete before provisioning. And so, at LANL, we've been experimenting with building open firmware using Linux Boot and uroot, the Go-based initramfs, in order to include a Kraken in our node firmware. And not just a Kraken, but the Kraken. So what is Kraken, you ask? Well, Kraken at a high level is a distributed automation tool that uses graph theory among other concepts to achieve a eventual consistency of a system. Though it's a generic automation tool, it was originally developed as a tool to more reliably provision stateless nodes. My co-author Lowell, the author of Kraken, presented earlier today on it, so if you want to know more about how Kraken works under the hood, and in theory, look there for further details on it, as well as the Kraken website and GitHub. It's worth noting that the core of Kraken itself is housed in the Kraken repository under the Kraken-HPC organization on GitHub, and the particular application of Kraken to managing clusters is housed under the Kraken-LayerCake repository under the same organization, and that is tailored to the purpose of provisioning nodes. And so, we have been experimenting with provisioning nodes from firmware by using Linux Boot to build a firmware image containing Kraken. We have dubbed this upcoming project Kraken Boot, and so far we've been able to build a customized OVMF image that runs a very basic version of Kraken, but are still figuring out the best way to support Kraken's extending features securely while addressing its size constraints. The project, though, is still in its infancy, so unfortunately I don't have a full demo quite yet as of this year, but next year I would like to at the very least have a minimal working example of bootstrapping a cluster through firmware, through power management, and hopefully even beyond that by actually provisioning nodes with operating system images. In the meantime, though, we have been working with the open source firmware community on improving the tooling to build these firmware images and the UEFI tooling for more boards so that more people like you can more easily build open firmware for your own systems. And so here are all the sources and further reading endnotes that I alluded to in the previous slides. Do check them out in looking to delve deeper into the topics that I discussed throughout this presentation. And so with that, I'd like to thank you for attending our presentation at LISA this year. If you have any further questions not addressed in the live Q&A, please feel free to email myself or my co-author Lowell. Do also feel free to join the Open Source Firmware Slack to ask more general questions related to open firmware and to join the community. We could definitely always use more help. Once again, thank you, and with that, enjoy the rest of the conference.